So good morning, California. Good afternoon, good evening, everyone, wherever you might be. It is my great honor and pleasure to welcome my mathematical father, Mark RIEFFEL. He was my supervisor in Berkeley, and I'm very grateful to him for all that he taught me. And now I am delighted to give him the floor, and he will speak about the convergence of Fourier truncations for compact quantum groups. Mark, the Zoom is yours. Take it away.
Thank you. I'm delighted to be here with all of you via Zoom. I have regretted not being able to participate in this seminar this fall because it has been meeting exactly during the time when I teach. And so when Piotr invited me to give a talk in the seminar, I told him that I couldn't because it met at the same time that I teach. And he, being a very clever fellow, very soon came back and said, well, surely you don't teach on the day just before the American Thanksgiving holiday. And he was right. So here I am.
Yeah, I got you.
Tomorrow being the Thanksgiving holiday. Anyway, very, very pleased to be here. Let's see, I guess I should go to the next slide, the outline of my talk. So as I say, following up on recent papers by Alain and Van Silicon and others, I'll sketch what I mean by Fourier truncations for compact quantum groups and giving several classes of examples. And then I'll discuss how one puts metric data on compact quantum groups. And here there are many open questions, but there are some answers. And then I'll indicate how, once one has suitable metric data, one can prove that the Fourier truncations converge to the metrized compact quantum group for a suitable kind of quantum Gromov-Hausdorff distance. So starting with a spectral triple, and where this topic really began to take off, one lets P be the projection onto a finite dimensional subspace of the Hilbert space that's spanned by eigenvectors of D, typically the lowest eigenvectors. Then PAP viewed as a space of operators on the P applied to the Hilbert space. That's an operator system, which is called a spectral truncation of the algebra. And Alain and Walter, they studied in detail the very rich structure of the spectral, the triple, the very basic one of the circle with its usual action and the usual Dirac operator. And they showed that if you normalize things so that the eigenvectors the eigenvalues are integers, and P is the projection corresponding to the eigenvalues minus n up to n, then the corresponding spectral truncation is the operator system of Toeplitz matrices of the appropriate side. And then they went on to show that the dual operator system is, under the Fourier transform, the operator system, which I denote A super n, of functions on the integers supported on the interval from minus n to n, acting on the little L2 space for the integers by the left regular representation. And it's appropriately called a Fourier truncation of A. That's what I'll take as my basic model for a Fourier truncation. And it's easily seen that the A super n's form a filtration of the algebra A. An interesting question that I've given no thought to, but it's certainly raised by this, is if you have a spectral truncation for a Dirac operator for a compact Riemannian manifold, how does one describe the dual operator system? So I say I've given no thought to that, but it's the obvious question to ask and who knows. So let's see. Going on, and the circle is, of course, the simplest connected Lie group. And if we take any compact Lie group, and Lie here is important, as we'll see. And if we look at the group C-star algebra and acting on itself by the left regular representation, and we let G hat be the set of all irreducible representations of G, and for any representation pi of G, we let A super hat be the corresponding isotypic components. For that setup, let's take S to be a finite subset of G hat, finite collection of irreducible representation, and take it stable under taking conjugates of representations and such that it contains the trivial representation. And we will require that the direct sum of the elements of S be a faithful representation of G. And this is where we need that G be a compact Lie group, so that it has a faithful finite dimensional representation. Then for each n, we can let S super n, and I'm laying this out so it's parallel to what I'm going to be doing in the other settings. Let this be the subset of G hat that consists of all irreducible representations that appear in the decomposition of the n-fold tensor products of elements of S. That includes shorter tensor products, since I included the trivial representation in the set S. And for each n, we can let A super n be the direct sum of the isotypic components of A for all representations in S super n. And then A super n is an operator system, which we again consider to be a Fourier truncation of A. And it's
I'm not sure, maybe can I interrupt with a question?
Yeah, go ahead.
Yes.
Yeah, I was lost when you wrote C star of G. You mean here the group C star algebra or the algebra of functions on G?
It's the group C star algebra.
The group C star algebra. Okay, so this story is about that. Thank you.
Yeah. Okay. So anyway, these form a filtration, and again, one can view this as a Fourier truncation. These are Fourier truncation of the thing. And somewhat more generally, if alpha is an ergodic action of G on a unital C star algebra B, and if for each n, each little n, each integer, we let B super n be the direct sum of the isotypic components of B for all representations in S super n, then again, B super n is a finite dimensional operator system, which we can consider to be a Fourier truncation of B. And again, we obtain a filtration. I mean, these results are certainly well known. Passing to a somewhat different case, if gamma is a discrete group, and if A is the reduced group C star algebra that's faithfully represented on the little L2 space of gamma by the left regular representation, we will require that gamma be finitely generated. That's I mean, the contrast between compact Lie groups and general compact groups is again this finite generation in a sense. So here we have gamma is finitely generated, and we let S be a finite generating subset of G that is stable under taking inverses and contains the identity element of gamma. I mean, but what's behind this, of course, is one can consider a corresponding, A as a corresponding quantum group, and then the elements of gamma itself give you the co-representations, but that's all to come. But again, this is parallel to what I'm the way I'm presenting all of this. So for each n, little n, we let S super n consist of all products of n elements of S, and we let A super n consist of the functions supported on S super n, viewed as a subset of A again. And then again, A super n is a finite dimensional operator system that we can consider to be a Fourier truncation of A, and the A super n's form a filtration of A. And yeah, as I say here, note that this C star algebra A has a co-multiplication for which it can be considered a compact quantum group. So then we turn to the more general case of compact quantum groups themselves, and there's no way that I have time to go through all the definitions and so on of compact quantum groups, but I will outline what I need. And what my notation will be. So I let A comma capital delta be compact quantum group, and capital delta, this is the co-multiplication that maps A into its minimal tensor product with itself. And I find comfortable notation about representations and so on is that A hat will denote the set of irreducible representations of the C star algebra A, which is not what we want our attention to. And I simply write delta with a hat on it to denote the irreducible unitary co-representations of this quantum group, and it's the co-representations that are what we need to examine. So we let A sub C denote the star algebra of coordinate elements of the coordinate elements of irreducible unitary co-representations of this quantum group. And basic result is that it's a dense subalgebra of A. And key element is that, well, a key piece of structure is that one has a Haar state, I'll denote by this small h, on this star algebra, and we can form the left regular representation on the GNS Hilbert space for the Haar state and extend that representation to A. And if this representation of A is faithful, then we say that the quantum group is reduced. And if this representation is also faithful on the universal enveloping C star algebra for A super C, then we say that the quantum group is co-amenable, and most of the results I have are in fact so far just for the co-amenable case. And as with ordinary representations of groups, one can decompose unitary co-representations into finite sums of irreducible unitary co-representations, and one can form tensor products of unitary co-representations. And then we can let S be a finite subset of delta hat that is stable under taking conjugates of co-representations, and that contains the trivial co-representation. And for each small n, we can let S super n be the set of all irreducible unitary co-representations that appear in the tensor product of n elements of S. And then if the union of all of these S sub n's, these collections of irreducible co-representations is all of delta hat, then we say that a delta is a compact matrix quantum group. And this is a slightly different way of saying the definition of a
I guess
compact
there
matrix
is one,
quantum.
Mark, I think there is one if, which is too much. You say then if, then we say.
Oh, yes, that's a little typo. Yes, thank you. Yes, and if we, yes, okay. Anyway, I mean well, I won't outline what the usual definition of compact matrix quantum group is, but it's certainly for those who know what that is, that it's very clear that then that implies this definition, and a little bit more is needed to go the other way. So then just as before, for each little n, we let A super n be the direct sum of the isotypic components of A for all elements of S super n. Again, this is isotypic components for these co-representations. And then each A sub n is a finite dimensional operator system for A. And if our compact quantum group is a compact matrix quantum group, then the A sub n's, well, their union will be dense in A, and we can consider them to be a filtration of A, and we call these again the Fourier truncations of A for this situation. And even more, if this quantum group has an action, an ergodic co-action of G on a unital C-star algebra B, then for each little n, we let B super n be the direct sum of the isotypic components of B for all elements of S super n. And then each B super n is going to be a finite dimensional operator system, finite dimensional because of the assumption of the action is ergodic. And we can consider, well, we consider these to be a form of Fourier truncations of B. As I said, they form a filtration.
Mark, may I ask you a speculative question?
Yes.
So what if you are not ergodic? Then would it be, say, finitely generated over the C-star algebra of coaction invariance? Like a finitely generated module?
I'm not fully understanding your question, but I can say certainly take the direct sum of two copies of B, and then that would not be ergodic, but you would still have this same structure. So the main issue is that you need, if you want your operator systems to be finite dimensional, then you need some condition that says that for whatever you're acting on, all of the isotypic components will be finite dimensional.
Yeah, but my feeling is that if you replace, say, ergodicity by just freeness, all right, so you are no longer finite dimensional, your isotypical components are no longer just simple vector spaces, they are finitely generated projective modules. And then I guess you would have, instead of finite dimensional vector space, finite generated projective module over this fixed point C-star subalgebra. I'm guessing, but that's how I view it.
Yeah, I haven't thought about that at all. That certainly would be interesting, and I guess yes, I guess they might well form a filtration in that case, and I don't know whether yeah, it would be interesting to see whether the results I have about convergence and so on would apply in that case.
Okay, yeah. Thank you.
So I have a question. May I?
Yes,
sure, go ahead.
By filtration, you mean a filtration which is compatible with multiplication? I suppose,
This action,
or not.
yeah, I mean, I think I said co-action.
No. B is a sister algebra. And
Yes, I have to say your audio is not coming in very clearly for me. But anyway, B is a C-star algebra.
yes, is this filtration compatible with multiplication in B?
Yes, it is. I mean, that's basically because
Okay. So the
how
filtration
tensor products decompose.
Mm-hmm. Can be anything said about the associated gradient of this filtration? Does it have a special form?
I have not looked at that at all.
Okay, thank you.
Okay. Any more questions?
I don't see any volunteers. No.
Okay. So, and here I say for a compact Lie group G, the unitary representation of G gives the co-representations of the C-star algebra and so on. So that all fits into this picture. So now we turn to the question: how do you put metric data on this situation? And the kind of metric data that I'm interested in is motivated by the process of attaching the Lipschitz constant, I noted L of F here, to a continuous function on a compact metric space. And this can certainly give the value plus infinity. So the definition, and I gave this definition some time ago in the slightly broader setting of ordered vector spaces. But here I'll just stick with operator systems. So let C be an operator system, and let L be a semi-norm on C, except that we do allow it to take value plus infinity, and there's no problem in understanding what that means. And we will say that L is a Lip norm, the Lip being for Lipschitz, on C if it has the following properties. That first of all, it should send elements to 0 if and only if the element is a scalar multiple of the identity element of, or the unit element of the operator system. And L should be stable under taking the adjoints of elements of the operator system. And then you do want that the set of elements for which this semi-norm is finite is dense, and it'll be a dense subspace. And it's convenient to have L be lower semi-continuous, and that even if you don't have lower semi-continuous, you can always pass to a lower semi-continuous one that has the properties that one wants. But then there's one further very crucial property that's more complicated, and let me explain that now. We look at the operator systems have a state space just as C-star algebras do. So we let S of C be the state space of C, and then much as Alain did for the semi-norm from the Dirac operator of the spectral triple, we set that what we use that to define a metric D super L on the state space by well, you see the formula there, D super L, but mu and nu are supposed to be states, and you look at the supremum of the difference of their values on various elements of C, for which L of C is less than or equal to 1. And without any further hypothesis, this distance can take value plus infinity, which certainly you don't want. but the final properties that we need is that the topology on the state space determined by the metric should coincide with the weak star topology, and in particular, that means that the topology from this metric does give you a compact space, and of course the metric has to be finite valued everywhere. So that's the basic definition of the data that I use that replaces having a metric on a space. And if you are looking at a compact ordinary metric space, and with L, it's a process of attaching Lipschitz seminorms, this fits this just fine, and you can from the seminorm you can recover the metric, so it's equivalent data. And this compactness it's crucial in a variety of ways, but for us it's crucial for defining the quantum Gromov-Hausdorff distance that we'll use. In ordinary quantum Gromov-Hausdorff distance is very much for compact spaces. So anyway, we will call a pair C comma L a metrized operator space. If C is an operator, oops, there's another, I don't know, that I wouldn't call that a typo. That should be operator system. C is an operator system, and L is a lip norm on C. So if you in fact have a C star algebra, and L is a lip norm on a C star algebra, so it satisfies all of those conditions, we'll say that L is a C star metric if L satisfies a further condition, namely the Leibniz inequality that you see written there. That certainly is I mean, without that, the seminorm L is really not having any particular relation with the multiplication in the algebra. And we call a pair a compact C star metric space if A is a unital C star and algebra, and L is a C star metric on A. And notice, this is pertinent for our filtrations, notice that if we have a metrized operator system C comma L, and if D is a sub-operator system of C, then when you restrict the lip norm to D, you again get well, you're going to get again a metrized operator system, and so in the particular case we're interested in is that you start out with a C star algebra with a lip norm on it, so it's a C star metric space, and then if C is a sub operator system of A, then the restriction of L to that sub operator system will give you a metrized operator system. So that's going to be the situation for our filtrations, our truncations, as we'll be starting out with the C star algebra, but then looking at the elements of the Fourier, the Fourier truncations, which will be sub-operator systems.
Mark, just one question.
Yeah.
Yes. When one considers the operator systems, it's very important to handle matrices in a compatible manner. So don't you have to impose some compatibility of the Lipschitz norm with the matrices in some way?
For what I need here, I don't really need
I
that.
understand. For what you need, no.
But
yes, okay.
Yes, I mean, that's certainly yeah. For other situations, yes, and I did publish a paper talking about matricial aspects of this.
Right.
That doesn't seem to enter into the picture
okay.
at this relatively primitive level. Other questions?
What do you mean? Because you will restrict ellipsis norm which is constructed globally to subsystems. So then the problem doesn't arise. This is what you have in mind. Huh?
Yes, that's right.
Okay. Okay. Perfect.
Okay. Okay. So yeah. So yeah. I guess I say here that if we have a C-star metric space and if the A sub m ends are some filtration of A by operator systems, and we let L sub n be the restriction of L to A sub m, then you can ask whether the sequence of these operator systems converges to A for some suitable notion of Gromov-Hausdorff distance, and that's our goal. And certainly, to get that, one has to put on more conditions. But as far as examples, so if we let G be a connected compact Lie group, I mean, I haven't needed connected earlier, but let's have it here just for convenience. For what you choose an add-invariant inner product on the Lie algebra of G, we can define a Dirac operator on D on a Hilbert space of spinors. I don't want to go in the details here. And then using that Dirac operator, exactly as Alain did, you define a semi-norm just by taking the norm of the commutator of the Dirac operator with the operators of pointwise multiplication on yes, this is my S here is my space of spinors, and standard results show that L super D is a lip norm that satisfies the Leibniz inequality, and so is a C-star metric, and it's invariant under translation and so on. So it's just a very, the restriction will then give you lip norms, and that's the classical situation. But we should note that the Leibniz inequality does not have any meaning for operator systems that are not C-star algebra. So you lose that aspect, and I don't I don't know of a good replacement for that, except possibly the matrix aspects of things. So getting into other examples that are related. If gamma is a finitely generated discrete group, as we had been discussing earlier, and if S is a finite generated subset of gamma that is stable under taking inverses and contains the identity element of gamma, then just as before, we let S super n consist of all products of n elements, and then what I hadn't mentioned before is that S determines a word length function, small l on G, by letting L of X be the smallest n such that your element X of this group is in your set S super n. And in Alain's first article concerned with metric aspects of non-commutative geometry, the main specific class of examples that he gave consists of the Hilbert space, the little L2 Hilbert space on the discrete group, and with G, the Dirac operator being pointwise multiplication by this length function.
I have a question. I'm a little bit confused. You have only one group, yes, gamma. Since you have also G on your side.
Oh, do I have another typo? Yes, that
It
should be
should
gamma.
be gamma everywhere, yes?
That should be gamma, yes. So
Okay.
the slash in front of the G to make it a gamma, I guess, got forgotten. Okay, yes, this is
Okay.
all right. So let's see. So the Dirac operator is pointwise multiplication by the length function, and the C-star algebra is the reduced C-star algebra acting by the left regular representation, and then as I've said before, he defined the semi-norm L on A by L of A is just the norm of the commutator of the Dirac operator. Now with the operator of the left regular representation, and this defines on the metric space. It defines a metric on the state space in the way that I've indicated above. That's invariant under left translation, but I'd probably say this on the next slide. Without further conditions, I mean, this metric could take the value plus infinity for all we know, and it's not clear. And oh, this L does satisfy the Leibniz inequality, but it's far from clear whether this important compactness condition holds about the metric giving the state space the weak operator, excuse me, the weak star topology. And at present, this is only known to be true in the case where gamma is z to the n, and the complication in that case is that there are all sorts of different generating sets that you can finite generating sets you can take, and their corresponding length functions and so on. But anyway, that I worked out in 02, and then in 05 with Ozawa, we did the case of hyperbolic groups, and then considerably more recently with my colleague Mike Christ, we did nilpotent groups, and in these three papers, the techniques in all three are very different, and so it's a mystery as to whether there's some unified framework in which all of this works, but that's the present status. So very much an open question is for which other finitely generated groups is the semi-norm defined above in terms of a finite generating set, and for which groups are those lip norms. So now what about lip norms for compact quantum groups? And results of mine from 02 show that for any separable operator system, there's an abundance of lip norms, and in 09, Hanfeng Li, as part of his study of ergodic actions of compact quantum groups, made the first study of lip norms on compact quantum groups. And for a compact quantum group, Li says that a lip norm on A is regular if it's finite on this dense star subalgebra of coordinate functions. And my 02 results imply that there is an abundance of regular lip norms on a separable compact quantum group. That's not saying anything about how these semi-norms relate to the co-multiplication. You would like them to relate in a way that is analogous to translation and to saying that they're translation invariant. And Li gives a definition for that a regular lip norm is left invariant. And I might say at this point that in looking through the literature for compact quantum groups, there seem to be some inconsistencies as to whether you view certain things as being left invariant or right invariant. But so some of the things I say, some people may think I should be saying right instead of left, and so on. Anyway, that L is left invariant if for every state we have this L on with this sort of convolution on the right, that's a norm non-increasing, and I give the definition of what this convolution is just in terms of the co-multiplication.
Yeah.
And Hanfeng has a nice proposition that if you're
sorry, Mark, I think I had the third typo.
Very likely. Where's there a typo?
In red.
Oh,
In red.
yes. Okay. Yes, didn't see that one. If your compact quantum group is co-amenable, and if L is a regular lip norm on A, then you can obtain a left invariant regular lip norm L prime by setting the taking L prime to be the supremum over all of the states of L on these right convolutions. And further, he went on and showed that if you then apply L prime for the corresponding left invariant construction to one of these right invariant construction for right invariant lip norms, you apply that to a left invariant one, then you get a bivariant regular lip norm. So that means that on any co-amenable group, you actually can have bi-invariant regular lip norms. But it's not at all clear whether any of these left invariant, much less the left bi-invariant ones, satisfy the Leibniz inequality. And so that's a big question. How can you characterize you certainly need separability and to even have the weak star topology metrized, but as long as you have that, which compact quantum groups have at least one left invariant C star metric? So I certainly don't know. I haven't given much thought to that, and certainly don't have any good conjectures about it. So that sets up what we have as far as metric data, and then we turn to how we define the distance between two metrized operator systems. And so let's let C and L super C be a metrized operator system, and similarly D and L super D. And what we do is we let M of L super C and L super D be the set of all the lip norms L on the direct sum of C and D, such that the quotient of L on C coincides with L super C, and similarly for D. And most people probably haven't seen the quotient of a semi-norm, but you define it exactly in the same way as you define the quotient of a norm. It all works just fine. And for once you have this condition that the quotient seminorm is the one on the particular metrized operator system, the consequence of that is that the inclusion of the state space of the operator system C into the operator system C direct sum with D, that is an isometry for the metric L super C on the state space of C and the metric D super L on the state space of the direct sum. And similarly for D. And so you can view the state space of C and the state space of D as submetric spaces of the metric space, the state space of C direct sum with D for the distance from L. And then by definition, the quantum Gromov-Hausdorff distance between C and D, and in some sense that notation should really be mentioning the seminorms also, but this is traditionally how one writes it. That the distance is very much just as in ordinary Gromov-Hausdorff distance. You look at all of these possible admissible seminorms L's in this class M, and you look in the state space of C direct sum D at these two submetric spaces, the state space of C and the state space of D. Those are both compact subsets of it, and you look at the ordinary Hausdorff distance between those subsets, and you then take the infimum over all possible L, and that's the definition. That's the fairly primitive definition of Gromov-Hausdorff distance that I gave, well, almost a couple of decades ago, and certainly in once you have C-star algebras and so on. Well, even in this situation, there are stronger versions, but for operator systems, I mean, this is
I have a
good choice.
question.
Yes, Tom.
Could you come back to the previous slide? Yes. So this distance is defined by the usual ordinary Hausdorff distance for state spaces of states.
Yeah.
But also the classical Gromov-Hausdorff space distance could be applied to spaces itself in the classical case. Okay.
Yeah.
You can speak about so this state space or space of state is like a space of probabilistic measures on a given compact space.
Yes.
And could you compare this Gromov distance Hausdorff for the spaces of states with the original classical Gromov-Hausdorff spaces of compact spaces?
Yes, and this distance in that case can be it's no bigger than the ordinary Gromov-Hausdorff distance, but it can be smaller because in effect for the ordinary Gromov-Hausdorff distance, you're really looking looking at the distances between the sets of pure states.
Yes.
You're only looking at points, and so you're asking for given a pure state in one of the spaces, how close is it to a pure state in the other space? And so that because of that, you may not be getting as small a quantity as if you're allowing the general states, which are going to be probability measures.
So in particular, you can have this quantum Gromov-Hausdorff distance equal to 0, even if quantum spaces, classical quantum spaces, completely different.
No, you're not. you're not going to have, no, they're going to give equivalent topologies on the state space, but not the same metrics.
Okay, thank you.
Okay. Any other questions?
I guess not.
So let's see, is this? No, now I'm where am I? Yeah, all right, we were here.
Mm-hmm.
Yes, okay. Oh, okay. Yeah, so for any particular examples to apply this, the challenge is to somehow construct lip norms on the direct sum of your two operator systems that bring their state spaces appropriately close together. And a convenient way of approaching this is to look for lip norms of the form L of C comma D being your L super C of little c, the lip norm on one operator space, the max of that with the lip norm on the other space, and then max some. It should be a semi-norm N C comma D for C and for little c and C and D and little d. Yeah, and this should be a norm continuous seminorm, and relating to the fact that Cn, because of the disjoint, the direct sum that you're taking there, you're really looking at sets that the state spaces don't overlap. There'll be a finite non-zero distance between them, and well, you certainly want it to be zero on the identity element for the operator systems and so on. But the crucial condition is this condition about having the quotient give you the original seminorms, and for that you need the condition that I've written at the bottom here, namely that given any c, little c and big C, and any epsilon greater than 0, there's going to exist some d such that L super big D of D, the maximum of that with N of C comma D, that has to be less than or equal to L super C of C plus epsilon. And similarly for C and D interchange. And a semi-norm with these properties is called a bridge. So looking for bridges with these properties is easier than tackling the whole question, and works fine. So going on, yeah, so we want to go in the direction of constructing bridges for our situation, and so we need some propositions here, and again, this is following what Hanfeng Li does, that because vector states of faithful representations of a C-star algebra are weak star dense in the state space, and because for a compact quantum group, the image of this dense subalgebra L sub C is going to be dense in the Hilbert space for the Haar state, we obtain the following proposition that if you have a compact quantum group and if L is a regular lip norm on A, and if we assume that our quantum group is in reduced form, so that its Haar state is faithful. And for any state on A and any epsilon, there's some other state of A and a finite subset of the irreducible co-representations, such that for any irreducible co-representation that's not in this finite set, the new state sends it to zero. So this new state is non-zero only on a finite number of isotypic components, and that the distance, basically the distance of this state and the new state is governed by the given lip norm with epsilon as a constant in there. I think you see the formula at the bottom there, and the proof of this result very much uses that the metric from L metrizes the weak star topology on. I think that's probably a typo there. It should be on the state space of A. No, I'm sorry. No, this is okay. No.
But I have a question. Could you please remind me what this AC is?
Oh, that's the dense star subalgebra of all coordinate elements from all irreducible co-representations. It's the standard dense star subalgebra that one has in any compact quantum group.
Okay, so that's this dense star-Hopf subalgebra, right?
Yes, exactly.
Okay. This is what we call the image of a Peter-Weil functor. And I'm having problems reading this sentence because for a compact quantum group, the image of AC in the genus Hilbert space for a Haar state dense. I'm missing something. For the Haar state dense.
Way up at the top.
Yeah. I think is dense, right?
Okay. Is dense. Yes, there should be an is in there for the Haar space. Is dense.
Okay.
Yes.
Good.
Another typo.
Yeah.
I only proofread this about 3 times, and there are always more typos.
Of course.
It's very discouraging. Anyway, yes. So anyway, this is crucial. This is where you're beginning to see finite approximations of things. Okay, and well, and yeah, if L is a compact, if you have your compact quantum group and alpha is again an ergodic action on a C-star algebra B. So I was just reminding what that means, that alpha is a star homomorphism from B into the minimal tensor product of B with A, and this includes the case in which A acts on itself on the left. So the results that I'm going to give below apply. You let you suppose L super A is a regular right invariant lip norm on A, and you assume that your quantum group is co-amenable, and you let L super B be defined as above, so that L super B is an alpha invariant regular lip norm on B. And if you if you let epsilon be the co-identity of A. Right, okay. So in this case, because my quantum group is co-amenable, the co-identity will be a state of your algebra. So this is another place where you use the co-amenability. Then using the proposition that was on the previous slide and some other results, we obtain the following crucial proposition that so let epsilon be given, and then you take the co-identity element and you use that as the mu of the earlier proposition was applied to any state, but now you apply it to the particular case where you're using the co-identity element as the state to produce a new state, nu, and the finite set of irreducible co-representations with the properties described in that proposition. So in particular, this state nu sends all isotypic components for representation not in F, it sends them to 0, that property. And then if we let P sub nu be the operator on B defined as by this sort of a left convolution where I've put the definition of this left convolution right on the same line with the equation. Okay. Then what happens is that the range of this operator is contained in the sub operator system B super F, the direct sum of all of the isotypic components for elements of F. And that's again going to be a finite dimensional space. And you have the inequalities that you see at the bottom, that when you apply this operator P sub nu to elements of B, it's semi-norm non-increasing, and that the amount by which it changes B in the amount in norm is less than or equal to epsilon times this semi-norm on B. So that's a crucial step, and again this is reflecting work of Hanfeng Li. Okay. And then the following theorem, which is our main theorem, it can be viewed as a generalization of a theorem of mine in 04. We actually use that. So I'll show that. I'll show that in a moment. It's the case for compact matrix. Well, it's the case just for ordinary compact Lie groups. So the theorem is, if you have a compact matrix quantum group, and if you have picked a finite subset S of the irreducible co-representations, and you want it again closed under taking conjugates of representations and as the identity representation. Okay. And you assume your compact quantum group is co-amenable. And if you let alpha be an ergodic action of this compact matrix quantum group on a unital C-star algebra B, and again you let L super A be a regular lip norm on A, which is right invariant, and you form the corresponding lip norm L super B for the regular, well, I mean, that will be a regular alpha invariant lip norm as defined earlier. So with all of that set up, then for each little n, we let L super n be the restriction of the lip norm on B to the operator system B super S super n, so that forms a metrized operator space. And then the theorem is that the distance between those operators, yeah, I should be saying operator system, the distance between these finite dimensional operator systems and B itself, the distance, the quantum Gromov-Hausdorff distance, that goes to 0 as n goes to infinity. So that's the main theorem. That's the convergence of these Fourier truncations to B itself for quantum Gromov-Hausdorff distance. And the just sketch of proof is that you let epsilon be given, and then according to the proposition above, we can arrange to find a state nu of A and a finite subset F of the co-representations, such that the range of P sub nu is contained in B super F, and you have these inequalities, just copying what I had before. And since this set F is finite, we can find a big N such that this finite set is contained in S super big N. And then for any little n beyond that, we still have F contained in the S super n. These S super n are increasing sets that increase up to the whole whole delta hat, and thus the range of this operator P sub nu is contained in each of these B super n's. And then we can immediately apply a proposition from that earlier paper of mine to conclude that the quantum Gromov-Hausdorff distance is less than epsilon for all n. And I'll show you that earlier result of mine. Well, yeah, the bridge that you use in this situation is simply to take epsilon inverse times the norm of B minus A. So it's very, very simple situation. And whoops, I thought all right, maybe I thought I'd included that earlier. Well, oh no, I'm sorry. This is yeah. Did I just do this? I mean, this is my earlier theorem.
Mm-hmm.
Yeah. Okay. Yeah. This is the earlier. This is the theorem from my earlier paper that applies directly to the proof of the main theorem that I had just given. Okay. And again, thank you for your presence.
Okay, thank you, Mark.
Any questions?
Yes, let's ask questions at will.
Okay, I mean, I guess I have the same type of question as I had before. Namely, it seems because you construct very explicitly the bridge and the Lipschitz norms that you have are obtained by restriction. So in fact, probably you are proving a stronger statement in the sense that you could impose on the Lipschitz norms that you consider further compatibilities. I mean, it's unclear how for operator systems, you know, what type of compatibility you have, but it should be true. I mean, yeah.
David Kerr and Hanfeng Li have a stronger version
Mhm.
of quantum Gromov-Hausdorff distance that does involve the matricial aspects.
Ah, okay, good. Okay.
And as I say, this paper is on the archive, by the way, and as I discuss in that paper, I'm pretty sure that
Sure.
this all works for their stronger version. I just that using that stronger version definitely would complicate the notation.
Of course, yeah,
Yeah.
sure.
Okay,
Any other
anybody else? Adam, Tomek?
Yes, I have a question.
Please, Adam.
Okay, thank you. So there is also this notion of a propinquity. Yes, this is due to
Yes.
Latre-Molière, and the main advantage of this notion is that the space of all possible quantum metric spaces is complete with respect to this distance. And I wonder how this situation is in this case of operator systems. So here in this quantum Gromov-Hausdorff distance, you also obtain a completeness result, or is it not true?
Yes, let me say first for those who aren't familiar with it, the Frédéric Latre-Moliere's propinquity, which does have these wonderful properties, it depends very strongly on having the Leibniz inequality. So it really only applies to C-star algebras, and so you can't apply it to operator systems that are not C-star algebras. But yes, for the quantum Gromov-Hausdorff distance that I've described, yes, you do have completeness also.
Okay, thank you.
And that's considerably more elementary than the completeness for the propinquity. But by the way, I mean, I certainly a very big question that I haven't mentioned here, but which is certainly more important is what about the convergence of the spectral truncations? And so, of course, what I've said here doesn't really say anything about convergence of the spectral truncations, and that's a very interesting question to be explored.
Okay, Tomek?
I have a comment and a question. So my comment is that if you have these operator subspaces forming a filtration compatible with multiplication, you could consider some approximation property with respect to this filtration compatible with multiplication. So now you are talking only about a system of operator subspaces. And you are talking about approximation in the sense of the system, maybe in general, not related even to multiplication in this algebra. So, but if you have this filtration, then the system of restrictions of your Lip norm to these operator subspaces somehow must be compatible with this multiplication. And then this system of restrictions of Lip norm could be abstracted. And an abstract analog of this system of this norm on some filtrations could be defined. And then there should be, maybe could be, a theorem about the good property of this kind of approximation in the sense of abstract approximation of this space of states by these operator systems. I'm not sure if I'm clear in my explanation. my impression that this point of view could be made a little bit more precise by considering not restrictions of a given global Lib norm, but by considering a system of this restriction to this filtration, and taking into consideration the compatibility of these restrictions with respect to multiplication. Didn't you consider this kind of approximation property?
I have not looked at that in this context. I believe that in La Tremelliere's work in connection with propinquity and so on, I believe he does have some results of that kind. But
I see.
But to what extent they would apply to operator systems, I have not given that any thought.
Okay, thank you. So at least my question was not crazy.
No.
So maybe I can add something to this as a comment.
Yes,
Go ahead. Go ahead.
So first of all, thanks very much. This is very great work. So there's this concerning these spectral truncations. There's only a few examples indeed where this seems to work, and maybe even just one, I don't know, which is the circle. But in that context, what I wrote is some kind of sequence of spectral triples, according to what you just mentioned, Tomac. So where you have some kind of compatibility, some maps between these systems and the system that you try to kind of approximate. And then there's a compatibility between the Lib norms, which you can just spell out, which ensures this convergence. And which is, I think, very similar, and maybe one can, since it's an inclusion, so one of those maps is just the identity, or the inclusion map, and then that would be automatic. But there seems to be kind of some control between all these systems at different stages of your, filtration or your truncation.
Okay,
I don't know if that's what you were after. But...
Thank you very much.
Yes, I have one small comment also concerning the the Leibniz inequality for operator systems, which is the following, which is that after all, operator systems have enveloping C-star algebras. And I mean, there would be a kind of naive definition of the inequality, which would be to say that you require that the Lipschitz norm that you are considering on the operator system would be obtained by restriction of a Leibniz Lipschitz norm on the enveloping C-star algebra. This might be too restrictive, but at least it shows that there are candidates, if you want, for the replacement of the Leibniz inequality.
Yeah. So one would like a theorem characterizing which Leibniz seminorms on an operator system come from.
Yeah, exactly. Which Lipschitz seminorm come from Leibniz seminorm on the enveloping C-star algebra.
Yes,
that's
exactly.
Yes.
That would be very interesting.
And then maybe you could do this propinquity on operator systems.
I mean, but another interesting question is, if at the C-star level, is if you have one of these Lip norms that does satisfy the Leibniz identity, when does it come from a spectral triple?
Yeah, of course. This is a very fundamental question. Yes. Yeah.
Yeah,
yes,
it's a very fundamental question, and not easy. Easy to answer, even in the commutative case, even in the case of commutative C-star algebra.
Yeah, certainly.
But Alain, there may be some tension, because so the representation you take for your operator system on, say, on a Hilbert space, on which the Dirac operator would also act, that does not need to be the one that realizes the C-star.
I completely agree. I completely agree with that. This is why I said it was naive, what I was saying, because I mean, okay, I was just making some statement which made sense, but I mean, as you say, one should have the freedom to use different Hilbert-space representations of the operator system in order to make a good statement. This is for sure true. I mean, yes. I mean, there is one also, at the conceptual level, there is one very interesting aspect of the bridges, which is that in some sense, they ought to be related to, you know, this idea of correspondence, which I had promoted a long time ago, which was bimodules. What I have in mind is that, in a way, I mean, a bridge is something like, you know, it's a very general notion of a map or morphism and so on. And similarly for the correspondences. And algebraically, I mean, the bimodules are very natural setup for correspondences. And I wonder whether they can play a role, at least to construct these bridges that you were considering. And especially, you know, in view of the bivariance theory, of the metric aspect of the bivariance theory. I mean, I am quite vague, but what I mean is that I think it's very interesting idea, the fact that when you construct a space which makes two different spaces very close because they are in a common space somehow, you know, this corresponds to, I mean, for instance, you know, I was always puzzled by the following fact that, after all, when we view the Higgs field in the standard model from two copies of the original space, I mean, the fact that, I mean, this is telling you that if you would allow the two spaces to have different metrics, this matrix would be extremely close in the Gromov-Hausdorff distance because of the Higgs mass.
Yeah.
So I mean, so what I mean is that, you know, there is a general line of ideas which has obviously to do with this notion of bridge that you have, and which I think is very, very interesting, which is to obtain between non-commutative spaces, more generally, a notion of morphism which is more flexible than just, you know, of course, you know, morphisms of C-star algebras or things of this type, which is far too restrictive. That's what I have in mind. So, I mean, of course, here it plays a role for the metric aspect, but certainly it should also, I think, Walter, you see what I have in mind because you have been working on such things. I mean, I'm a little bit vague, but.
Yes, I can see. I mean, this you want the kind of the unbounded picture to
Exactly.
realize a leap norm.
Exactly. And using the Dirac operator of the unbounded picture, perhaps to construct the bridge. I don't know if this, you see.
Yeah, that's interesting, yeah.
You see, because after all, I mean, we use the Dirac operator to construct the matrix. So why not use the spectral, I mean, the bivariance theory to construct the bridge? Because on the other hand, okay, the bridge is very symmetrical. So this is different from, because I guess, Mark, when you construct the bridge, there is not one space which plays a different role from the other. It's entirely reflexive, entirely symmetric, I guess.
That's right.
Yeah. So this is the difference. This is the difference with the bivariant. But however, for the bimodules, it's entirely symmetrical. So my question, Mark, is more the following: when you construct bridges, would there be a way to associate to a bridge a bimodule and something like a Dirac operator on the bimodule? You know, that would make things more, you know, sort of Hilbert-space theoretical. This is my question. Yes.
Yes, I certainly understand, and I sense that may be some of that maybe behind some of the construction of specific bridges that have been constructed, but
Well, that would be great. Yes. Yeah.
I don't see the general picture at the moment.
Okay, Tomek.
So first, I would like to ask Alain, do you mean, I remember from Frédéric Latremorier's talk about bridges that he considers something which is called pivot, pivot element. And if I remember well, these pivots can be understood entirely in the language of bimodules, as Alain said.
Okay. Oh well, that's a very good point. Okay.
Yeah. So
I don't know. I don't know.
Yeah.
I cannot answer. Mark can answer, but not me. I mean, you know.
Well, I agree that the pivot, I mean, again, this is in this setting of C-star algebras and doesn't really apply to operator systems, but yes, the pivot looks very much like some generalization of a Dirac operator in some sense.
Yes.
And I mean, I had earlier put on the archive a paper about Dirac operators for matrix algebras that converge to coadjoint orbits, and in that paper I have a section which isn't entirely satisfactory. I mean, it's near the end in which I do for the bridges in that paper, I do produce a Dirac type operator that uses the the actual Dirac operators on the matrix algebras and the coadjoint orbit, and uses the pivot as part of the Dirac operator on the direct sum of them. So
okay, well, okay, that's very good. That's perfect.
Yeah.
Yes. Yeah.
May I comment about this?
Go ahead.
So this opens a very attractive perspective, because if the pivot is a weakened version of a Dirac operator, maybe there is some Leibniz-like version of spectral geometry, spectral triplets, and all this business in the language of pivots instead of Dirac operators. I remember there is a theory of, for instance, Sobolev spaces on metric spaces. I know a guy, his name is Piotr Hajłasz, he's a colleague of mine. He introduced some very nice theory of Sobolev spaces without differentiation, entirely in frames of metric structure. And I see some parallel flavor of this theory and MARC's theory of Leibniz leap norms. So maybe there's some archetypical spectral theory for such Dirac-like pivots, incompletely metric version of spectral triples.
Well, you know, I just want to answer a little bit there, because I mean, certainly you will catch the metric aspect with this, which is perfect and which works very well and which tells you a lot about spaces and all that. But somehow, still, if you want, you will not be catching something which is absolutely essential, at least if we want to connect with physics. And if you want, which is the key property of manifolds. And I think I have to explain this, because I wrote it several times, but in this context, it's quite important to mention it. I mean, if you want, what people have found gradually over many years of fight with, they were trying to understand what is a manifold, not locally, because locally it's obvious. I mean, locally, okay, it's just a piece of Euclidean space, so there is no mystery. But they wanted to understand what it means to be a manifold globally. And of course, I mean, then the first properties that you encounter when you, I'm talking about a closed compact manifold, oriented and everything, okay? So the first property that they encountered was the fact that you have Poincare duality, okay? And then they tried to say, okay, might be a manifold is a space, okay, which has Poincare duality up to homotopy and all that, okay? They tried that. And what was shown, if you want, is that, okay, in the simply connected space, what you do, you put the space in Euclidean space, and then you try to wiggle it a little bit so that it becomes a smooth manifold. And what you find out is that the difficulty in order to do this little wiggling is that you have to promote the normal micro bundle. It's not a vector bundle, it's a micro bundle. So it's something which is looking like a vector space, but only up to homomorphism. So it's very, very bad. So you want to promote this micro bundle into a vector bundle. If you could promote this micro bundle into a vector bundle, then you could use Thom transversality and you would be back to a good manifold, to a true manifold. Mm-hmm. So then people thought about this, they did a lot of work and so on. And Sullivan in the 1970s was able to find exactly the obstruction to promote this micro bundle into a vector bundle. And amazingly, what he found is that this obstruction is KO homology. And at the same time, Atiyah and Singer were working on the index theorem, and they found out, if you want, that the cycles in KO homology, they are represented with Hilbert space operators. And this is why, if you want, the content with the Dirac operator is not only the metric, but it's also the fundamental class in KO homology. Mm-hmm. And so, I mean, you can, of course, look at one aspect, but if you look at one aspect and you keep in mind the mental pictures that you have, where you have the complete picture, then you are misled. We have to keep the whole package together. But what I found extremely nice, for instance, with these bridges and so on, it seems to me, if you want, that the Dirac operator for the standard model, it's really the bridge between the two sides. So, I mean, and we have to understand this much better. I mean, we are just, we are exploring things. Okay, fine. And I believe that indeed, by trying to find the right concepts each time, okay, we shall make real progress. I mean, but as I said, there is this lesson from the past about the fundamental role of KO homology and of Hilbert space. And this is really the contribution of Atiyah and Singer, I mean, from the index theory. Because before, I mean, nobody would have believed that Hilbert space had anything to do with, homological algebra or things of this type. I mean, they were all working with simplicial complexes and such like that, things of this type. They had no interest in Hilbert space, but no, Hilbert space play a crucial role because of cycles in KO homology.
Well, of course, one of the problems with one of the deficiencies of Gromov-Hausdorff distance is it totally ignores topology, and any compact space can be approximated as closely as you want by a finite set of finite subset and so on, and so it's not going to see any of the homological properties and so on. Right. And I don't know what a good remedy for that is.
Well, in a way, it should be a combination of the two. Namely, if you know the metric, then knowing the metric, you have asked before, Mark, the fundamental question, you can ask, can you realize this metric from Dirac operators and so on? And this will give you an extremely strong constraint on the type of Dirac operators that you want to construct. To that constraint, you could add the fact that you wanted to realize the K-homology fundamental class. Then you would have, you would have two constraints which would be extremely strong. And then, okay, you might minimize some spectral action and get a good realization. I mean, and this is exactly what physicists are, in a sense, trying to do. I mean, we understand space-time, we understand somehow, the metric aspect and so on. But, and I think it's Riemann who said that probably, we are using the continuum to approximate something which is really finite. But it's not probably it's not finite as a set of points, but I would suggest that it's finite as an operator system, finite dimensional, I mean, because finite as a set of points, it is already dismissed by people who are doing cosmology. They know that it's not a good idea to approximate space evolving and so on with a finite set of points, because then you get into contradictions very, very quickly, actually. But of course, when we use operator systems, the flexibility is immensely larger than that. So,
yeah.
Sorry, may I have a question related to this comment? So we would like rather expect that this operator system would be this Dirac operator system, or maybe this dual, this Fourier, since these two are not the same. Yes.
No, not at all. No. We don't know. I mean, one has total freedom. This is the rule. There is no dogma.
I see.
Okay. Anybody else would like to weigh in?
If I could comment, it would be a comment to the comment of Alain about the indispensability of this kind of differential structure, at least in the sense of this microbundle. It's very interesting that in this theory of Sobolev spaces, of metric spaces, you can speak about non-trivial homotopy classes of harmonic maps between manifolds. So maybe it's not on the same level as KO cycles. Maybe it's some higher version of invariance, because these are topological invariants of spaces of map, rather than about topology of the space itself. But still, there is some topology hidden in consideration of this Sobolev spaces of map. These are Sobolev spaces of mappings between spaces.
Yeah, in fact, in what you say, it's probably dual. You see, because what happens is that you want to look at maps and take harmonic maps and so on. So this will represent like you will consider like ordinary manifolds. You will map them into your space, and then you will take some harmonic condition and so on and so forth. But somehow, if you want the K-homology class, which is global, which is like with the Dirac, is like the dual to that. So you should be able to pair the two things, but not, they won't be the same. They will be dual to each other, I think.
Maybe, yes. But I have a different thought about this. If the Dirac operator is something like quantum mechanics on a given manifold, then these homotopies of spaces of mappings between manifold, it's like field theory, quantum field theory, something like this.
No, I mean, well, okay. I mean, it's I understand what you have in mind, but I understand what you have in mind is that because you consider spaces of maps, it's more like a space of fields and so on. Certainly, but yeah, but I mean, the Dirac operator, if you want, it really plays the role of the, how to say, I mean, of the propagator for the one particle space. It's not quantum mechanics. It's really the core of quantum field theory. Really, that's the role that it has. It's already connected to quantum field theory directly.
Yeah. That's true. Yeah, that's true. I have another question to Mark about the relationship between this states and pure space. I don't understand the relationship between these Lip norms and the convex structure of the space of states. If I don't have this compatibility between these two, I cannot understand what is happening to external points, to the pure states. Can be said anything about this compatibility between these Lip norms and the convex structure of the space of states?
I'm not quite sure what you have in mind, but one thing that is the case is that you can have different Lip norms that give the same distances on the pure states, but not on the non-pure states. Already in the commutative case. So that's an interesting phenomenon. Knowing what the distances are between the pure states is not enough to know what happens to distances between all states.
Yeah, but I suppose it's a purely quantum phenomenon for non-commutative setting.
No, I'm saying already just for the functions on a finite set, and for a Lip norm given by a Dirac operator construction, you get this you can get this problem.
I see. Yes.
Not a quantum.
Finite sets are classical, of course.
Completely classical finite. Yeah. There's an example of that in I think it's my paper from 2002.
But if I can comment, as far as I remember, it was mentioned by Frédéric Latemoliere that this mapping, which maps a metric space X with a metric D into C of X with this Lipschitz seminorm coming from this metric D, is a homeomorphism onto its image. So this is a topological embedding. So not only, okay, it is continuous, first of all, then it is injective, but also the inverse from the image is also continuous. But I don't know whether it is uniformly continuous, since it doesn't make sense to pose this question. And for this, I don't know.
I certainly don't know.
So this is about topology, but not about this uniform structure.
Yeah, it could be so. Even in the classical case, this state space can also be equipped with this Monch-Kantorovich, yes, distance.
Yes.
Yes.
Okay.
Okay. Anybody else? I don't see any volunteers. So I know we already had a lot of questions, but please allow me to have very quick 2 questions, Mark. Could you go one slide back? 1 or 2? Let's try 1 first. Yeah, 1 more. Yeah, I'm looking at your main theorem. So you have this beautiful approximation result, and I'm just wondering, maybe just completely naive, if you want to analyze this distance between different sister algebras, A and B, and for both of them you have this sort of approximation by these operator systems, maybe you could use it as a tool to prove, I don't know, that the distance between A and B is 0, if it happens that somehow these BSNs and ASNs are close enough to each other. Would it be a correct way of thinking that you could somehow, in order to attack the question at the global level of a sister algebra, do it at this partial level for a given n?
Yes, and I haven't thought about this in the setting of operator systems, but I believe that in Frédéric's work that there are results of that kind, and
Okay.
that he can, from which he can get a certain mileage. But I mean, it's hard to verify the conditions that he needs for that.
Okay. So it wasn't a completely crazy idea. And now it's well, just tangentially related to your talk, but you mentioned these ergodic actions. So this is like Galois objects in Hove algebras. And a canonical example is, of course, classical torus acting on a quantum torus. But I'm having troubles imagining non-trivial cases where you'd have a compact quantum group acting ergodically on a sister algebra, which is different from this compact quantum group. Can you give me some examples? I was searching my mind and I couldn't find it. And I remember that studying such things, say, for SLQ2 in the algebraic context was very hard. And the funny algebras that were obtained as a result of classification were very non-amenable to function analysis. I mean, no bounded representations and stuff like this. So I know if I take SLQ2, what would be a sister algebra on which SLQ2 would act ergodically, and except for SLQ2 sister
Well, the Podlich spheres.
But it's not. Oh, so you give up freeness. You just want transitive. Okay, sorry. Okay, yeah, that's
yeah.
Okay. So then it's you can go. You have zillions.
Yeah, there are lots of potential examples for quantum homogeneous spaces, but
yeah.
That's a complicated subject, and again, finding Dirac operators for quantum homogeneous spaces is certainly has been been slow progress, is my impression.
Yeah, I just misread it. Ergodic and free. So my mistake. Sorry.
Yeah.
Tomek, you still want something?
Yes, I have a question about the notation used in the proof of this main theorem. Your operator P nu is denoted in such a way that one could ask, what if P nu is a projection? Which is the case, because P nu is a kind of averaging. It's a convolution with a state. Yeah. And if this is an idempotent, the projection with respect to this convolution, it means that it corresponds to some subgroup, morally speaking.
Yes, okay. And I mean these are more like the Fourier kernels, and so on. And I mean, using a truncation is, I think, too harsh a technique to work in this kind of context. I don't know whether I'm really answering your question, but yeah, I mean, I think one doesn't want to look for projections.
So if this
goes back to the problem for Fourier series. If you simply chop off a Fourier series and ask for convergence there, you have difficulties.
So it's
be more subtle and use Fourier kernels for convergence and so on.
So my question is not natural in this context to consider the case when P nu is a projection. Convolution projection.
No.
Okay.
No, I don't. Yeah, I don't.
Okay.
I don't think so.
Okay, thank you.
Oh, Adam, okay.
Maybe one last question. So there is also one sort of examples where you approximate something which is commutative by something non-commutative, and this sort of examples comes from the theory of deformation quantizations. So are there any results of Gromov-Hausdorff convergence of such deformations?
Well, I mean, certainly in the case of the non-commutative tori, there are.
Yes, but I mean this deformation with H bar. Really, this deformation quantization.
Yeah, well, I mean, the quantum tori form would fall within that framework.
Yeah, exactly. Yes.
Okay.
So, yeah, I think Hanfen Lee showed that for the Conwandi spheres and so on.
Okay, so
yeah,
this parameter Q from this non-commutative torus is like a e to the minus h bar,
Yeah.
something like that.
Yes, of course,
okay.
of course.
Okay.
Yeah.
So h bar goes to 0, then q goes to 1. Yes, and
Correct. Yes, of course.
Yeah, exactly.
Recovers the classical situation. Okay. Thank you.
Okay, guys, I think it's time to wind it up, and let me do it on a funny note before we thank Mark again. So we were discussing symmetry of bridges, and Mark, correct me if I'm wrong. I remember that if you look at the Golden Gate Bridge, you have 5 lanes, right, on the Golden Gate Bridge, and 3 lanes go to San Francisco, but only 2 lanes go out of San Francisco. So that's a bridge which is not symmetric.
Mm-hmm. Yeah.
Sorry, I couldn't resist it to end on a Berkeley note.
Yeah.
So let's thank Mark again for a wonderful talk and a very good discussion. Thank you, Mark.
Okay. Thank you, Mark. Yes.
Very much my pleasure. Very much my pleasure. Well, and to see so many familiar faces.
Yeah. Well, it was a genuine reunion. So now let me stop recording.